So lastly, we have Alexei Miasnikov, professor at Stevens Institute of Technology. A number of years ago, he collaborated with Gilbert Baumslag to develop a software system for computing with infinite groups. And at the same time, Alexei founded a startup called Gradarius, which is an online and active learning platform for mathematics, powered by technology that understands much more than just correct answers. So Alexei will tell about it. So therefore, Alexei will primarily discuss the educational aspects of AI and mathematics. So absolutely different topics, not about work of mathematician, but about education. So Alexei, you can start.
Thank you very much, Elena. Thank you for inviting to give a talk at this workshop. And okay, so I will talk about math education and how we can improve it. So there is math teaching and teaching mathematicians. These are very different things. I will talk about both of them. The first one, just for this talk, it will be something about how to teach high school algebra or calculus 1, say. And another one is how to teach mathematicians, thinking about we are teaching, say, graduate students in math. And there are kind of big challenges right now in both. As mathematicians, we know that, yeah, that there are a lot of problems here. What I will talk about, I will start with math teaching and end with teaching mathematicians. And my focus will be how to use technology, in particular AI, in this. But before we can answer how to use AI or not to use AI, we need to kind of try to discuss the questions. What is the ideal model of math teaching, say, for high school or undergraduate teaching at universities? When we are teaching our PhD, say, students, we need to at least know something about how mathematicians will do math in the near future. So that's what I will try to address in this talk. As Lena said, I have some experience in creating software which helps to teach elementary or fundamental math. It means calculus 1, say. When I came to Stevens, I was tasked to improve teaching of calculus. And that's where we started. Instead of just hiring a lot of good teachers, what we did, we tried to develop some software which will sort of mimic or help teachers to teach calculus. And about the second part, I also was part of the, at that time it was called machine learning, to prove some mathematical, solve some open questions, in particular, whitehead minimization problem using machine learning. So I will talk mostly about my experience here and what we did with Gradarius, the software we developed. So if you talk to teachers or professors or educators right now, basically the communities consists of two large groups. The first one believes that ChatGPT or LLMs is the solution to most challenges, and if not now, but in few years, you don't need any other technology and you can just use, say, ChatGPT. And if you think the main reason is, of course, first of all, it's impressive that the success LLMs have. It's impressive, but also there are only finitely many problems in math education now. So something like ChatGPT can learn them all and learn how to help. So there is a reason to this. And the second group, which believe that ChatGPT is completely useless, even bad for mass education. So the viewpoint that I would like to advocate here is we need technology in teaching. And of course, we used it all the time. And breakthrough were sort of using chalk and then books, computers and internet. I thought it will be much more, but it's, and now AI, which is a really good technologies, and whether we can successfully, again, use AI or not, that's the question. So from my viewpoint, we don't need to talk about replacing teachers by AI, but the main principle, we would like to outsource the routine to machines and leave teachers do the rest, which is, from my viewpoint, is the most interesting part, really. You to do motivation, discussing fundamental concepts or general strategies, how to solve problems of this type, discuss point of views, express something. So a lot of things a good teacher can do besides explaining how to do steps in very particular problem. That's what we tried to do at Stevens, and to some extent we succeeded, because that was the first time in my life our professors were saying, oh, now I have a lot of time in lectures. I am not Russian. I'm not in a hurry. I have time to explain things. So machines will be helping teaching, not replacing them. And the warning here that it changes teaching. So teachers will need to understand the technology and be able to use it. And moreover, they should manage the machine. So I believe one of the reasons people like ChatGPT, because it's very easy to work with it. You don't need to do anything. You're just asking questions. So I don't want to discuss everything, how you teach math. It's too much. But I would like to focus on solving problems, which I think is the most important activity when you learn in math, and the most difficult to learn. How I will look at it for this talk. It's very simple. So to solve a problem, a student needs to produce a sequence of elementary logical steps that leads to the final answer. It's not like in Kevin's talk from axioms to something. No, it's some sequence which other students or teacher can understand. And important thing that the learning occurs when students not just repeating steps that they know, but when they try to invent some steps on their own. So if your problem is just one step, it's an exercise. It's not a problem from every point. So you need to invent several steps maybe. This could be difficult, and if you can't do it, it's frustrating and it's discouraging, really. So what is the ideal teaching model for this? It's imagine that you have a teacher who has just good teacher who has just one student, and he or she works with this student all the time. So it's one-on-one. It might be for students, it's good to participate in some projects and competitions, so on, but I will focus just on this from the teacher's viewpoint. So there are two types of activities here still. There is a so-called inner loop, when a student is solving a problem, and whatever he does during the solution is inner loop, inside a process of solving a particular problem. And the teacher is looking and helping student in real time. What does it mean? Teacher showing errors, giving hints, explaining maybe some key points, managing the student's learning experience. It means he should kind of intervene when frustration builds up, for example, or make sure that it's interesting to some extent. So keep engagement, asking questions. I don't know, it's up to the teacher, and so on. And motivating students to do it. So it's not automatic. Whether you show immediately when the error is made, or you wait, or when you give hints and so on. There are a lot of things here, but these are activities with good teacher is doing during the inner loop. There is also outer loop. When think about it, students just doing many problems during the course and other things. So the teacher ideally knows all the data about students' problem solving and navigates the students through the course. So it includes choosing the right problem to do next. That's very important, I think, because if student is solving a problem, you give him next problem which is too easy or almost the same as student just did. It's not very interesting, maybe boring. Or you do it too difficult problem and students can't do it. So it's discouraging. Student losing confidence and it's frustrated. So it's important thing, but also it's not just that. It's you're solving a problem of remediation because you noticed the students are missing there are some gaps in his knowledge or her knowledge. And you would like to remediate doing some problems. Or also, you're not just giving a million of problems. You pick a problem, next problem, which is the most advantageous to students in terms of efficacy, how students go through the course. So it's not easy. It's a complex activity, outer loop as well. So what we embarked at Stevens Institute when I started this project a long time ago, some time ago, we wanted to have an automatic tutor that does all these things, helping students when they are solving problems. And we thought that it's a homework tool. We would like to outsource involvement of human teachers to homework, sort of automated tutor, which helps students do the homework. So it's inner loop hints, feedback, and grading, and outer loop, it's a personalized learning trajectory through the course, and students were supposed to, software was supposed to be able to communicate with students in some nice way, kind of get it engaged, and actually it should be supposed to be a communication between students and software. That were 3 goals. So we created Gradarius and I would like to discuss this is for the talk. Gradarius is just an example what you can do and what is good, what is bad, and so on. So first of all, it should be step-by-step feedback and guidance. So interface should be allowing students to put whatever students want in the free form, and it should be step-by-step. So you can software looks what students do and can help. to help, it should be, we realized you need to model what is solution of a problem. It's not just a sequence of steps because it's much more complicated. It could be smaller steps, bigger steps. It could be different types of solutions and so on. It's much more involved than just a sequence of steps if you would like to really model the solution. And to do the auto loop, you need to have a knowledge space of the subject or a course. We did something and it helped. It improved in retention, which was very important for the university because it's about money. And we improved retention, not lowering the standards, academic standards, which was very important for us. And surprisingly for me, teachers received much better overall, much better evaluations from their students. So what is involved, this platform? So it's several levels. First of all, the platform or algorithms can see the solution process for one problem. That's in the loop. We can see data from history of students' problem solving, all problems which were solved up to this point, say. And it's very important that we see not just the final answer or final solution, but we see how students interact. A particular student interacts with software, gets a hint, changes, corrects the solution, and so on. All the work, all the history. And also we can see how students in the course do it all together, or maybe other courses, what are kind of typical data. You can see all students' data involved in the course. So what is the solution? How we model the solution? So it's three vertices. So it's a hypergraph, and vertices are some mathematical expressions, and it could be tables, could be whatever. It could be a graph of function and whatever. It's vertices, and from one to another, there is a elementary transformation sort of. If you apply this transformation to this vertex, you can get something in the other vertex. It's elementary step in the solution, very, very elementary. And everything is tagged by vertices, transformation, is tagged by learning objectives or skills, whatever it is. So it's a hypergraph, directed hypergraph is vertices like that, and edges, hyper edges labeled by transformations. So there are elementary transformations, very small ones, and there are big steps, like you're discussing how to solve problem in big steps, strategy sort of. It's another hyper edge, which consists in maybe of, so that's the picture. For example, computing the minimum of a function on an interval. This is on the left, it's a description of some big steps. And on the right is a hypergraph. And the color, for example, blue color here, it's compute derivatives, a big step. So it's a hyper edge which contains a lot of small steps, small solutions, small elementary steps of the solution that students can do. And it's usually much more detailed than students maybe do, because you need to see the mistakes and you need to remember, we need to give feedback about mistakes and also hints. So all this information, this hypergraph. Important thing, it's like what, yeah. So there are a lot of interesting and difficult algorithmic problems which occur here. It's students is doing something, making mistakes, maybe doing something which is not clear why, and going sort of wandering in the forest. But at every moment you need to locate where student is, his position or her position in the solution, this solution graph, solution hypergraph. To help, we need to know where the student is in the trajectory of the solution. It's not very easy. There are some methods, but it's interesting and quite difficult problem, algorithmic problem. So this is about inner loop. So choosing the right, as I said, choosing the right problem, deciding what kind of remediation is required, and continuous assessment. We are not given a grade, say. We would like to see what the current students' knowledge state, whatever it's a subgraph of the knowledge. Yeah, I didn't say. So we model the whole course or the whole subject as a huge hypergraph, and this is knowledge space for the subject. So we would like to, in assessment students' knowledge, we would like to locate student current knowledge state inside this huge knowledge space for the whole subject. So what is this knowledge space? You start with the standard sort of prerequisite graph. Something what was Kevin again was talking. To know this or to prove this, you need to prove this. So it's to know A, you need to know B. Say there is a age, directed age from one to another. It's a skeleton, and some other, there are such knowledge graphs for different subjects. For high school algebra, it's famous ALEX program. And there is a, for example, Cambridge University framework for mathematics. It's different, but it's something similar. But what we want to have a space which is designed for checking solutions and problem solving. So on this standard graph, we glue solution hypergraph to the proper places related to the vertices. Vertices of the skeleton are learning objectives, and we put it there. So for us, as I said, learning objectives could be notions, definitions, could be particular problems, could be actually mistakes, typical mistakes are also there. It's learning kind of, it's a atom. So we glue, idea is to glue hypergraphs to the skeleton, and you will get a huge knowledge space of the project. So I would like to say that formalization, so it's like, I liked it during Kevin's talk at formalization in lean. Here it's also kind of formalization, and a lot of things it's done by hands, manually, especially at the beginning. But the difference is we are not formalizing some language, we are building algorithms, and they can be connected from little routines. You can connect to build more sophisticated algorithms, so on, to do the problem consisting of a sub-problem. It's a hyperage. So you can combine this algorithm and get new algorithms. So it's formalization basically means that you have all the algorithms in place somehow. Now you can use AI or to combine algorithms and expand. So I don't want to get into it right now. So we built these things and it worked to some extent, but there was a obvious kind of limitation. We knew, or the software knew what the mistake is, knew mathematically precisely what the mistake is, or what is the next step students should do in his problem solving process. But it was dry mathematical thing, and you need to tell students in proper way. As I explained, even in the inner loops, there are a lot of things good teacher is doing besides checking whether it's correct or not. Whether it's correct or not, it's not really that difficult. You can have some, I don't know, symbolic algebra system doing it like. So there are a lot of things involved, how you communicate. And we were struggling because you need to code. If it's deterministic, you just code in all these communication strategies, and there are a lot of them. It's unbelievable how much recommendations, for example, when you teach intermediate algebra or something like 6th grade pre-algebra even, there are a lot of things from pedagogy coming, how you give a hint. I never knew it. It's immense. So that was a problem. And LLMs now allow Gradarius to reduce time and effort to test and implement new communication strategies. But it turns out to communicate with the student, it's a big important problem. Even suppose software knows what to say mathematically. And then ChatGPT appeared, and clearly you can communicate with it. It's very easy. You ask questions, you get answers. You can ask new questions, other questions, and you communicate very nicely. And immediately idea was, you don't need all this technology anymore because just use ChatGPT or any other LLMs. You can train them and use them and discard everything else. Of course, even Bill Gates famously said that, yeah, ChatGPT does not know math, and it's a problem. But so there are a lot of things which ChatGPT doesn't know. But let's go to very basic sort of things first. In math, there is a zero tolerance to mistakes. AI being probabilistic, it will do math mistakes or mistakes given a wrong hint or something else, because that's the nature of probabilistic things. So let's see how it works. Suppose you have an LLM which makes 99% of math problems correctly. It's a very good result. We are not there yet, but suppose. So you have a class of 100 students, which is typical, not even large class by modern standards. And you give them every week homework of 10 problems, maybe less, but say 10, easier to calculate numbers. So 1% of wrong solutions, it means you're getting about 10 angry students per week. So during the semester, you will have a lot of angry students who are complaining to you, to everybody. So it's really, from the teacher's viewpoint, it's unacceptable. So very easy solution is actually, don't ask LLM to do what is not really necessarily. Don't do some iterative mathematical algorithms. Just combine it with math solver, like Wolfram Alpha or SymPy or something else, or Gradarius. No point to invent a bicycle again, just because you would like to have pure LLM, nothing else. So you have fast deterministic algorithms to solve math problems. Use them. That's a first sort of thing. And it seems like it's a reasonable solution. And then there were experiments here. It's a paper. You can look the link to the paper here. So it turns out that without math solver, LLMs, they are very detrimental for math learning. So you do something and tests are much worse than the standard sort of teaching. They're helping you. It seems like you understand, but you go to the test and you're failing. It's not surprising because it does not understand math, sort of. Surprising thing, not really surprising, but another thing is that with a math solver, AI, at best is no progress, no improvement. It's kind of useless still. If you think, and if you look at the activities which I outlined above, what good teachers do, of course, AI in math solver doesn't do most of them. It just gives you correct, checks your little steps, whether it's correct or not. It's not, as I said, it's not really how you learn solving math problems. So it's not enough. The point is, there is much more than just checking correct little steps, logical steps in learning process. And the learning process, it's a well-organized thing. It's, as I said, from remediation and efficacy, which is difficult maybe, to controlling motivation or engagement or frustration, to thinking about what are strategies and so on. So there is another thing. There is a type of activity that every teacher actually does in a sense. It's I called it math tutor engine. It's something which organizes the learning process for students. So the real solution is, from my viewpoint, is something like you have LLM plus math solver plus math tutor doing things together. So LLM can communicate, and this ChatGPT, the chat part is extremely important here. Whatever math solver and math tutor, and they are mostly deterministic algorithms. Not really, but mostly it should be based on deterministic things that you have already created. So you have the learning space, knowledge space, you have all this technology. But communicating with the student, you need ChatGPT. And math tutor basically organizes this communication. There is no chance that students can organize themselves. They are asking questions, but you can ask questions from ChatGPT, but students who need help, they can't ask proper questions. They can't formalize their questions. They're asking something which is very often not really what they want, you think they would want to ask. So the process should be organized, and that's a math tutor here. And math solver, it works with math tutor and LLM and verifies the answers on little steps or solve them and provides step-by-step solution if needed. And that's the whole architecture, I think, which is required. So to end this part of the talk, what I think it's achievable to create automatic tutor, which will help real teachers to outsource the routine, especially in homeworks like that. But we need this, and it requires quite a lot of technology, and it's not that easy, it seems. But I think it's doable. Okay. Now, quickly to the second part. Preparing next generation mathematicians. So what skills next generation of mathematicians will need? It depends, of course, what will be the mathematical practice in near future. I personally, after working on this big software project with Gilbert Baumslag for NSF, I always ask my PhD students, doesn't matter what they do, it should be interesting abstract research. I do group theory or something like that, so it should be there. Plus, they should learn how to program in several languages, including something like C++ and Python. And lately I was asking, before I was asking about pattern recognition, have some knowledge or machine learning, now it's AI. Even though it's not related to it was not related to their PhD thesis, of course. Sometimes it was actually, but it was good. On the other hand, if you look back, quite a lot of my PhD students, after defending PhD thesis, instead of staying in academia and they had some opportunities, they went to the industry like Google to high-level positions, interesting positions, or New York Stock Exchange. So it was pity in a sense, but they work now as mathematicians. Okay. So the first thing I would like to say, it's math and computer science are getting much closer together. It's not by chance, because discretization and algorithmization in math is the dominating trends according to National Science Council of United States. I got some examples here from NP-complete problems in computer science, kind of in discrete optimization, to study NP-complete problem in math. It's a typical thing right now. Or from math to computer science, from homotopy theory, it's homotopy type theory in logic and CS. It's Voevodsky kind of approach. So it's changing. Instead of mathematicians sitting in a quiet place and doing math with his books, which I personally like a lot this way, it's changing to a mathematician doing his math with his collaborators, but also managing a team of robots in a close interaction. So I believe that in the near future, you will have all robots helping you. Robots, I mean something AI which can easily write programs for you. And we heard it in these talks today. Or helping to prove, sort of outsource routine proofs to the machine, or doing something else. So the crucial, again, point from how I understand it, we have a new ability to quickly create various computer programs and run them on various platforms to outsource the routine, get insights, and speed up the whole process. Before, you need to ask your students or do it yourself to write a program, run it, and change, and so on. It takes time. So there are three components in this activity. The first is kind of, I would call the experimental math. Quite often, if you start solving a math problem, you try something, some little examples, just to get a feeling, to have a little sort of put your hands on the problem. I think it will be big part of the problem solving. You can use programming robots, programming via AI, and wide libraries of math algorithms and data science algorithms like Mathematica, Maple, whatever you want. And you can do really experimental math. So you can think about experiments, ask programming robots to program it, run it somewhere in, I don't know, Amazon servers, and start analyzing the results almost immediately using, again, all the tools from data science at your disposal. It looks like experimental physics. So next generation mathematicians should be able to understand all and be able to use all these tools. It's a big change. And outsource the routine improving, providing proofs for kind of routine statements. And I don't want to get much more about this because we had Kevin's talk today, and I think it will be very useful and important tool when your area of research will be formalized. So, but you will need to learn how to do it, and I believe also the form of proofs, how you do it and how you write it, it will change too. If it will be, the Lean will be the leading sort of software for this, it will be to match Lean kind of format to some extent. But how you make your definitions and so on, it will change. It will change if you're using these tools. So it's a big change actually. And the last thing, which I think very interesting, using AI in finding conjectures. So if you got a good conjecture of why something is going on with your problems, it's a big thing. So you have experimental math, you can do experiments, and it will be sort of some tools for you to help us find interesting conjectures. And what Sergei Gukov was talking this morning about that. There are very interesting things here to say and to discuss. I don't have time, but the philosophy from my viewpoint is the following. You run some experiments and you can do it quickly because you can program and change and run much faster now. So suppose you're getting better and better algorithms for something. You don't know why it's going on, but you see some algorithms do it faster, or more examples. So if you have some irregular or non-random behavior, which is observed during experiments, it must be some mathematical reason behind this. So now you need to find it, and maybe it will tell you what the real conjecture is. So that's basically how I would think this finding conjecture robots in some sense will work. I'm talking about robots. Of course, they're not robots in sort of Chapeks who coined the term. It's some software which helps you to do all these things in a very interactive sort of environment. Thank you very much.